here because we don't have a lot of data, and so we want to find the optimal parameters by basically giving sort of rewards for different sort of states that we see and actions that are happening within the learning process, right? So we're able to basically in real time calibrate the prediction of the zoom, focus, and contrast on the microscope, right? And which helps with the real time, quality optimization on the microscope. So, and also if you look at the figure, we're able to see this process is happening with the human on the loop. So there is basically ability to have the human confirm certain actions and rewards and sort of tell the objectives with which the reinforcement learning has to learn or get a sort of end objective, right? And so the agent basically receives rewards for actions that result in sort of more optimal images, and iteratively it's refining its strategy, and then we'll find the optimal solution over time, right? So another approach we are looking at is based on imitation learning. So this is more like trying to imitate an expert who would look at this in terms of analyzing, right, what we were doing human in the loop. So we're trying to mimic the expert here. So in this case, again, we take the same metrics from the segmentation, the 5 metrics that we talked about, and then we are able to put it in this sort of test prediction phases, where we are able to do learning using different types of models that are using imitation learning, and we use sort of a trained model and a prediction model that is again doing the same thing we wanted in the RL case, which is predict the zoom, focus, and contrast. And the hope is that the prediction will get us the next best image, right, that will be necessary in the next iteration of the image acquisition to proceed with the way the CNT manufacturing has to happen in sort of the objective that has to be met, right? So these two are the algorithms that are driving the closed loop feedback. And how we have implemented this system is we have basically a set of web services that you can see here that run at the instrument to automate the instrument control, and we have basically what's called as a Python programmable interface, a PPI, with which we can automate the zoom or other sort of actions on the microscope, and then the data that's collected is able to be pulled out to a cloudlet, we call it, which is basically a very secure way to access the instrument, move data from the instrument out to some sort of a storage service that can then be used to do the analytics, right? So, so the physical security of the instrument is protected via the network connection through the sort of cloudlets that we are using. On the SEM side, we have a SEM cloudlet. On the storage side, we have a storage cloudlet. And so this infrastructure services, right, will drive other set of services. So we have here, as you can see, a whole set of security services that I will talk about a little bit more. But because we are remotely controlling these instruments, that could be hundreds of thousands of dollars, and little mishandling could be very expensive to fix. And also we want the data to be very securely stored, moved, and analyzed. So we use a number of security strategies to ensure the remote access, and then the resource management, right, to run the models, to get the feedback, to do the image storage management. All of that will be another set of services that will be about running. And on top of it is the portal web services, where we have the chatbot, the workspace for the researcher, the monitoring, auditing, and all of this is again through some sort of secure identity and access management, right, for the sessions. We're able to interface with the users, right, who can then set up monitor experiments, evaluate commands, give feedback options, and maybe even give some human on the loop feedback, right, to have a control or sort of influence on the various steps of the closed loop design we showed. So this is sort of the system architecture, and a little bit more detail on how the security is. But as I said, it's a very important aspect of building a remote system like this that's used for AI and automation. And so here you can see we are securing everything from the communication to the storage to the computation to a different set of services and APIs that ensure basically resilience against different types of attacks like cross-site request forgery attacks or dinner of service attacks or man-in-the-middle attacks, right? So we're able to also produce sort of encrypted connections between all of the various important components, and then have access control to deliver the right privacy, like who can see what data, what commands can be run, and who can run those commands and all of those things. Right? So it's a very cloud-led based secure architecture that is also a very important aspect of our implementation. And so we put this whole system that we developed in a test bed with actual instruments, with the whole storage service deployed on Amazon Web Services, and then image and AI training is on the GPUs within our MU cluster. We call it the Lewis cluster, and the researchers have a web portal access through the chatbot interface to basically, as I said, monitor, guide the experiments, look at the results, and provide human-on-the-loop feedback. And so this sort of test bed is used for our experiments. And here is the interface for our test bed. So we have chatbot, like we talked about, is going to give guidance on the zoom, contrast, and focus based on the algorithms. And then the users can look at the image, see the output for the prediction, and then use that to run the different experiments, right? So they can manage it through their sort of project interface or the workspace we talked about. So all of this is actually implemented, and we have a sort of closed loop with the set of instruments that support the Python programmable interface. And so we've collected a lot of data based on the system, and we're using it to train the reinforcement learning and the imitation learning algorithms. And we have a number of different images with different magnification levels, focus values, contrast values, and we have the 5 metrics, right, from the segmentation that are critical for our prediction of the zoom, focus, and contrast. And these agents essentially are using those sort of metrics to do these predictions. And then we have basically this data set to evaluate. And here are the kind of the results we saw, where we've compared the reinforcement learning approach with the imitation learning approach. And what we found it's very promising that both these approaches can really actually help do this sort of guidance of the real-time image analytics, and can help improve the CNT synthesis process in terms of better parameter selection, more sustainable and more accurate material property manufacturing. But we found that the RL approach actually particularly had certain limitations, right, given the type of data sets and challenges we had. But IL had better performance in terms of the zoom focus predictions, but had a little bit difficulties in the contrast. But in spite of these results, we can still see that both these methods can be very interesting and are alternatives that you can use, even though you have sort of limited data and you're trying to really solve a very challenging prediction problem for this sort of CNT manufacturing. So with that, I want to sort of conclude by saying that what we've shown in the remote instrumentation science environment is using AI methods like RL and IL agents can be really effective for real-time image processing that can help with manufacturing CNTs. And this process again involves both simulation and experiment. And this kind of a feedback system is not only relevant for CNT. You can use it, as I said in the beginning, for manufacturing polymers or LEDs or other kinds of material related manufacturing. And the key part is how we can employ this automation as well as remote instrumentation services in a secure and more automated manner to guide these experiments in an iterative process, and we're continuing to explore more advanced techniques like multi-agent reinforcement learning, and we've had some better results than this RL approach that I just showed you. So we're still continuing to improve the AI to do the predictions, but ultimately, I think our implementation as well experiments show that we can have the sort of very effective human-machine or AI collaboration, and by interfacing the scientific instruments to the analysis, as well as having a chatbot interface to get human feedback, is a very effective process, right, that we can use to do more futuristic materials manufacturing. And so, as I said, as future work, we're still looking at different kinds of RL methods. We're also starting to use a lot of large language models where we can exploit existing literature of certain synthesis experiments that can then be used to guide the human feedback in a more productive way, and that can actually even further improve how we can more accurately pick their CM parameters to guide the experiments towards the desired manufacturing targets. And so we're looking at, as I said, applying this to other materials, and this process obviously is something is as good as the knowledge base we're building with it, so which is also something we're doing, and we're looking at a variety of different other strategies in the CNT synthesis growth based on the sort of real-time conditions, and looking at how we can optimize the synthesis chamber properties and continue to develop these sort of schemes. So with that, I want to conclude and see if you have any questions.